So this is the 2018 Higher Triple paper for Year 10. This is going to be a two-part video. So it's part one because it's quite a lengthy paper. Here's your equation sheet at the front for page 2. And then we start off with an electricity question. So what we got going on here is a power source with a bulb. And then another circuit. This is a light-dependent resistor. So this is the resistance on this is going to change as the amount of light changes. So if I was to move this whole thing back a bit, the light intensity isn't going to be as strong. So there's a specific distance from the bulb to the light-dependent resistor there, and then you've got this thing is going to measure the resistance. So the two variables, other than using the same components, that should be controlled. That distance between this bulb and that light-dependent resistor has got to be the same. And I would say the same amount of light in the room. So if you're doing this in a classroom with the windows, with the blinds up, then the light is this is gonna be affected by the light from the windows as well. So you need the same amount of light. We can improve it by enclosing the lamp and the LDR in some sort of darkened container or in a dark room to limit the amount of ambient light that's available there. So we've got a set of results. We've got watts against kilo ohms. So it's important to note that's a kilo ohm. And then we've got a graph for 4 marks. So we're going to do the scale. You get a mark for the scale. You get a mark for plotting, and then you get a mark for this curve. Now, it is a dodgy curve because you can see that it kind of shoots up there. So just do the best you can with this. Always do it in pencil and make it one line. So it says in the mark scheme, no hairy lines. So it's got to be one confident line. You can see that I'm dipping there, which is not good. And then it's got some questions relating to the graph. So we're going to have to pick out now the resistance when the power is 10 watts. And just notice they want this in ohms, and we're giving it in kilo ohms. So when it's when the power is 10, I've come up and I've come back across, and that's around about 2.6 kilo ohms, which is the same as 2,600 ohms. So when you're going from big to small, you multiply. Suggested when the lamp power doubles, the LDR resistance halves. Now we can use the graph. So it's not a proportional graph. So you need a straight line for one thing to either double and the other thing to double, or one thing to double and the other thing halves. So that's called inversely proportional. And then you've got directly proportional. Because there's a curve on this graph, you're not going to get that relationship. Oops, sorry. So I've done a couple of calculations here. So I've said at 10 watts, the resistance is 2,600 ohms, which we've just calculated there. But when I drop it to 5 watts, the resistance is 4,800, and that's not double that. Okay, so the suggestion is wrong. So the statement's wrong there. Be careful, because the first time I did it, I went from 10 to 20, and it did come out at half. I think it came out as 1,300 ohms. So it does work in places. I think it's going to, because this line looks fairly proportional. So you've just got to be careful there. Just keep going with the calculations if you're getting that. It's connected to another circuit. The voltage is 2.8 volts. Current is milliamps now, 0.35 milliamps. So be smart, mate, stop being down. I'm going from now small to big, so I need to divide by 1,000. Or you can just use from page 1, or page 2 I should say, these prefixes here. So I can see that a milli is just times 10 to the power 3. So that's all I've done here. I've just stuck it in the calculator as 0.35 times 10 to the power 3, and I'm going to come out with 8,000 ohms. That's your first question then. Question 2 is all about the earthquake and the epicenter. So usually questions like this are based on text or some numeracy. In this case, it's just previous knowledge, so what we've learnt. So surface waves travel the fastest. That's wrong, because it is primary waves that travel the fastest. S waves travel on the surface of the Earth. That's wrong, because the surface waves travel on the surface of the Earth. S waves are transverse waves. Yes, correct. and P waves are longitudinal. P waves travel through solids and liquids. Yes, they do. It's only the S waves that can't travel through liquid. And then P waves are longitudinal waves. Yep, that's right. If S waves are transverse, S waves cause the most damage. No, that is the surface waves there. So 3 ticks for 3 marks. Just be aware. Just look at how many marks these tick boxes are worth. I've got a graph then with a primary and a secondary wave coming up. You can see the primary distance from the epicenter. So there's the distance and there's the time. So you can see that it's received at the same distance but quicker. So if we pick 8 kilometers there, or 8 times 10 to the power 3 kilometers, you can see that this P wave is the fastest one. Then we're given the seismograms, and we've got to first interpret the scale. That's going to help us then answer the questions down by here. So the first one for BC, I need to know what time the P wave arrives. So if I'm using this scale, I can see that BC, the primary waves, is there, which is a 16. So it goes from 15 minutes, 16, 17, 18, 19, 20 minutes. Be careful when we're writing these. We've got to put hours, minutes, seconds. So it's 00 hours, 16 minutes, 00. And then this box, it wants you the difference. So you can see here the difference between 23 minutes and 50 seconds between 19 minutes is 4 minutes, 50 seconds. So we're working in time here. So we've just got to be careful when we subtract one from the other that we don't just do it like we normally would with maths. We've got to make sure that every 60 it changes then to 19. So when we're doing the calculation for this, just make sure that we're working, in fact, in 60s for the 60 minutes. So it's 2 minutes 40 is the time difference. This one was a tough question because you're meant to recognize the relationship. There's no other way you can get it. So we tried doing it from the graph. And if anyone can do this, please drop a comment or come and tell me that the pattern that because there's been about 8 teachers on this. And the only way we can get it close to 1.6, which is what's on the mark scheme, is to convert these to seconds and then divide. So what we've done is converted this to seconds, 220 seconds, and we can see there is distance of 2.2. So the ratio there is 100, okay? So when we put 160 over 100, it comes out to be 1.6 when we convert that to 160 seconds. It's only a mark, and I don't think many people got that right. In fact, I'd have to check. I don't think any people got that right. So a dodgy question, but it's only worth a mark. And then we've got a nice 3 marks here. And what you would do, you'd use your compass and you'd measure the scale, and you get the distance obviously from this table, I think. Where did we get the distance from? Yeah, I've got the distances from here, but that's times 10 to the power 3, see? So we're going to multiply that by 1,000, and I've written them there. So 3,200 kilometers, 1,600, which is what we worked out, and then 2,200 kilometers. I'm going to put my compass on this scale, and I'm just going to draw these arcs, and then it's where it meets, where the 3 meet is going to be your epicenter. I got 2 more questions then, and I'll go to part 2 then. So this is a density question. This is one on irregular shaped objects where you would submerge the object in water to find the volume. So it's given us a massive solid, which is 26 grams. The volume of water in the measuring cylinder before you put the object in is 40. And then once you've put the object in, it's going to displace that water by 8 centimeters. You can see there's a difference in volume of 8 centimeters. And we've got the grams 26 on top. Just check that we're okay. So it's grams per centimeter cubed. Sometimes it's once in kilograms per meter cubed, and then conversions are needed. But in this case, we're fine for 3 marks. A nice, easy 3 marks, if you ask me. Describe how you would change the experiment to find the density of an irregularly shaped object that floated on water. So the whole point of this now, you've got to submerge this object in water for it to be displaced. In order to do that, you're going to have to use some sort of pointer, but you're going to have to determine the total volume of the pointer as well. So I've said use an object, pardon me, or a pointer to submerge an object. That doesn't make sense, does it? So you use a pointer like a pencil to submerge the object. So if you're using a pebble, you're going to push that pebble down with a pencil. Determine the total volume displaced by the solid and the object. So what I mean by that is like the total displacement of the pencil as well if you're using a pencil. And then determine the volume of the object used, so you subtract from one from the other. Particles in a solid are more closely packed, so there are more particles per volume in water is the answer to the next one. Explain in terms of particles why most solids have a greater density in water, because there's more particles packed closely. On to question 4 then, the advantages of a ring main circuit. So because there's 2 paths for the current, the cables can be made thinner. Each part of the cable carries less current, and that's why they can be made thinner, because current flows 2 ways. And then sockets can be placed anywhere, and each socket is going to have 230 volts then, because it acts like a parallel circuit. This again, because it says fault-free, caught a couple of us up. But I think this stops working when additional fault-free appliance is plugged into it. It's all about recognizing that it's going to be a power surge. So there's going to be a current surge, too much current. So you're going to use an MCB or a fuse. These both detect current surges. So again, a really funny question there, with 2 marks. If the lawnmower accidentally cuts the power cable, it's going to be RCCB then, because it's going to protect the user. So that earth wire is going to take the current, and then the difference is going to be detected by this RCB, and then it's going to switch off between the live and neutral wire. If a fault develops, so this explaining careful case required. Okay, if a fault develops, live wire touching, for example, the earth was going to take that current safely to the ground, because metal is a good conductor, and it can easily pass electrical charge to the user. Plastic is a good insulator, so it does not require an earth. I've just added on there because it wants to know why plastic does not need an earth. And that's it for this part. So tune in for part 2 when we go through questions 5 to 7, I think.